Hello students, welcome to EduCell. This time we are actually working on a next phase of recursion tree method. The previous lecture is all about the simpler recurrence relation solution we are doing using a recursion tree method. This time we are a little bit modifying the cost from constant to some linear. Suppose n could be the answer, could be we can in future will take log n, we can in future will take n square, log n square like this, or log square n. Okay, so like this that could be a next part of the videos. Next we are actually modifying the which the previous video is all about the constant. Now we are just changing the program as to a little bit more difficult, you can say, not that much difficult, little bit difficult we are adding. Next, what are the procedures, what are the steps that we want to follow? Okay, with the same one that we will start again. Okay, if n is equal to 1, here uh, we can write n by 2 instead of constant. I'm just using n. Okay, if I'm using n, then how we are dealing with this? Okay, simple. It can better we can go for it. Like here a floor function is added. Now 2 you can write 2, that could be better. Okay, then we work on a different way. Okay, if n is greater than 1, this is one formula, this is one function. Suppose you can remove 2 for a while, only this much is written, and you are going to use the recursion tree method. Okay, you simple write tn. Here you can ask me, so before that the previous lecture we are having constant, that's why we are writing the function. Can we write the cost directly, because cost is actually playing a vital role? Can we write? I can say definitely it will be. Okay, you can remove the cost, because for tn the cost, if you are going to expand the next, so here the floor or any ceiling is written, simply you write as n by 2. That's why I'm just using that one. Okay, no need to be getting confused, because if floor or ceiling is written, you take as a whole. Okay, that's why I'm just taking this example. So if you want, like we previously have one child, if you want to take 2, you can go for a 2. If you are writing 2, so 2 times the function is getting called. Okay, so first of all we are focusing here for the one child, and with the cost it is changing. Now cost is n, so once you are going for expansion of it, so better you remove the function and write the cost, because that time it was a problem for us. That's why we are actually not going to change it. Best condition for those I am telling are watching this video, kindly watch the previous video, which is simpler video, part 1 of it. This is a part 2 video where we are actually working with us. Little bit difficulty we are adding, but previous videos if you can check, they're the best thing, or the simpler way you can understand, because cost was there as constant. Here cost is linear, n is linear. Okay, now the condition, base condition is t of 1 equal to 1. Why that you know? Because n is 1, so in place of n you can put 1, so the value is 1. Okay, here next is, if you are going to expand, the cost would be n by 2. If you are asking sir how n by 2, then you can put the value of n by 2 in place of n, then it will be n by 2 by 2 plus n ke jagah n by 2 likh lo, done. So n by 2 will be the cost for tn. When you are expanding tn by 2, instead of tn by 2 you are writing tn by 2. Simple. So like this what you have to write, thus the next function would be tn by 4. Why? How? That you have seen. Okay, so tn by 4, if you are checking the cost, because you are going to expand it. Okay, so in this case what you are writing, tn by 4 by 2 plus you can write n instead of n, you are writing n by 4. The cost indirectly you have to write if you are going to expand it, and for this the next value would be tn by 8. So that's why we are writing under this, because it is unknown for us. Okay, now you're expanding this one, n by 4. Now it will be n by 8 dot dot. Okay, towards the constant we are running, because towards the base condition we are running. Okay, so now we have to write the left hand side and the right hand side. Here, cost per level. Okay, cost per level will be written here. Number of leaf, a number of nodes could be better. Number of nodes per level. Okay, so number of nodes per level you have to mention here. Cost per each level that you are going to mention. Okay, but how many times we are running? K times we are running. Okay, k times. If you are running for k times, what should we write there? यहाँ पे देखो level 0. Okay, for level 0 it is 1. For level 2 or level 1 it is 1. L2, for level 2 it is also 1. Level 3 it is 1. Like for k times if it is running, what do we write? Try to find a pattern. यहाँ पे क्या है? 2 to the power 1. Instead of 4, can we write 2 to the power 2? Yes. Instead of 8, can we write 2 to the power 3? Yes. These 3 देखो, level 3 यहाँ पे 3, level 2 यहाँ पे 2, level 1 here is also 1. Done. If level 0, if you are say, so where is 2 to the power 0? 2 to the power 0 is 1. N by 1 you can write, not an issue. Why? Because n is n by 1 also you can write. So that's why you can write or you can omit, but you should know the pattern is there. Okay, if for k times you are running, that could be at level k. Okay, so here you can write 2 to the power k. Why? Because for each level you are just running for that region. This is done. Now the number of nodes would be 1. Okay, and we say for k times, we say the cost is the base condition it is running. As per the base condition, the cost is 1. So you can write this one, or else you can write t of 1 dot dot t of 1, like means you have reached the base condition. Okay, so then cost per level. Cost per level is n. Simple. Here you are writing that one. Here is the cost. Cost is n by 2. Here the cost is n by 2 square. Here the cost is n by 2 cube, because I told you these are the cost. Now the cost is 2 to the power n by 2 to the power k. Okay, this is what you have to write. 50% of the work is over. Next part is, what is CLCI? Before that you have to assume you reached the base condition. Assume you have reached the base condition. Base condition is declared as t of 1 is 1. Now t of 1 is this one, t of n by 2 to the power k, which is your function. You reached up to k times. When you are running for k times, you are indirectly reaching the base condition. Why? Because base condition is easier for us to assuming. Why? Because base condition is having the proper answer with us is 1. Then we can equate with 1. Then we can expect this many times it is running. Okay, for that reason we are using the base condition. Now you can write 2 to the power k equal to 1. Why? Because the cost is 1 there, and here the cost of this is n by 2 to the power k. Okay, the cost will be equate once the function will be equated well, then only the cost will be equated. Then n equal to 2 to the power k. Done. This is equation 1 or 2 you can put. Next, to find the value of k, that we said it is 2 written here, that's why it's better you can add log base 2, you can multiply log base 2 at each the side. Log base 2 n, next log base 2 2 to the power k. Here k is, as per the logarithmic property, the power will be the front. Okay, So log n base 2 into k log 2 base 2. K log base 2 is 1. So you can simply say k equal to log n base 2. Simple. That you know. Now we are having CL, which is number of leaf nodes, leaf or last nodes, into cost of each leaf or last node. So number of leaf nodes will be how much? Here is 1 1 1. So leaf node is, or last node is 1. So this is your last node or leaf node. So last node or leaf node 1, simply you write this one. Cost for each leaf node. Cost means you have already reached the final one. The base condition cost will be applied as the cost of each leaf node because you reached it. That's why. Then CL will be 1. Here we are not using mathematical condition. You remember it's a constant is getting multiplied with a constant. That's why we are writing. If 0 will be written as a constant, we can say a 1 or 0 or C. Okay, constant is there. So, but you do not worry about the mathematical one. If you're multiplying 0, the answer could be wrong. Okay, then CI is the sum of all intermediate nodes. So to represent that, number of labels into cost per label. Okay, this is what you have to find. Number of labels are k times your running, so number of label is k. Cost for each label, or else you can go for a better conditions like better multiplying with this. You can go for by just adding this because sum of all sum of all intermediate nodes, better you can write sum of all intermediate nodes. So if you are taking sum of all intermediate nodes as per this, we can solve it better. Don't be confused because I told you like CL is number of leaf nodes, or you can say it's a cost of each leaf node will be multiplied with the number of leaf nodes. It's a cost of leaf nodes basically. CL is cost of leaf node. CI is sum of all intermediate nodes. Sum of all intermediate nodes. When you are actually adding the sum of all intermediate nodes, this time n by 2, n by 2 square, n by 2 cube, like this, it will be added. N plus n by 2 square plus n by 2 to the power q, n by 2 to the power 4 might be the next one. So n by 2 to the power k. Okay. Then what the next step? N is getting multiplied with 1, the first one. Okay. Next n you can write 1 by 2 square I can write. Then n into 1 by 2 cube also I can write. This one also being written like this. Okay, the fourth one if you want to write, so it could be n into 1 by 2 to the power 4 because n by 4 is like this, dot dot, plus n into 1 by 2 to the power k. Simple, you can write in this manner also. Okay, okay, done. Now again I am just simplifying it. I can write this one. Why? Because it's 0 1 I can write. Now I can write 1 by 2 to the power square because 1 square is 1, 1 by 2 square. Okay, n into 1 by 2 to the power 3 dot dot n into 1 by 2 to the power 1 by uh, this much I can write. Okay, now in the next page we are going to solve it. Okay. Ci is n, you take common, not an issue. 1 by 2 is 0 plus 1 by 2 to the power 1 plus you can take also 1 by 2 square, 1 by 2 cube plus 1 by 2 to the power 4. If you want to write here also 4, uh, n 1 by 2 4 plus dot dot. So here you can take this as common. Next 1 by 2 to the power k. Okay, this is done. Now n you have already taken as common. So here this is a GP process. GP, what we have to do, we have to formulate. In GP, the A is the first one. Okay, A is the first one, which is 1. 1. So A, the formula I'm writing, A by 1 minus R if R is less than 1. A, the formula A by R minus 1 if R is greater than 1. Done. This is how we are actually finding. See here, what is R? R is 1 by 2, 1 by 2, because 1 by 2 is getting multiplied. So AR 0, then AR 1, AR to the power 2, AR cube, like this. Okay. So here A is 1, next 1, and R is 1 by 2, though R is 1 by 2, which is less than 1. So what we have to apply? If this is one first formula, this is second formula, so we are applying the first formula. Okay, this is our formula which I am writing as note. Okay, so here we are applying this 1 by 2 and we close this. So n here, to simplify, if you are going to simplify this one, it could be written as this 2 minus 1 by 2. Again I'm just simplifying it. 2 will be the upper one, 2 by 2 minus 1 is 1. Okay, so it's 2n. Clear? So I'm just writing it, ci is 2n. Now time complexity. Time complexity is cl plus ci. Cl is constant that you found, it's just a constant. Ci is 2n. So the time complexity will be n you have written. Okay, you can simply write big of n. Theoretically it is correct. If you are saying big of c plus c into n, also the correct answer. Okay, because it's theoretically correct and it's practically correct. Sometimes the constant is getting added and constant is getting multiplied with the n, which is a variable. This is also a correct answer. Okay, next phase in decreasing, we will check here. In decreasing, suppose the same example which we have taken, we will take that one. If n is equal to 0, okay, and tn minus 1 plus n if n is greater than 1, suppose 0, better. Now you have to go for the solution using recurrence relation. This is base condition. The base condition is all about like t of 0 equal to 0. Instead of n, you are putting the value. That's why if n equal to 0, that is why you are getting the base condition. Okay. Now using recurrence relation, using recursion tree method to solve this recurrence relation, we can write T of n. Then what you have to do, you have to find the cost of T of n. Cost, it is written as n. The cost is written and you are going to expand it. Better when you are expanding it, you are writing the cost, then you expand, because this is there in the core man book which is written by the MIT professors. Okay, so here n by 2, the next function will be n minus 1. Why? Because it is unknown term for us. Okay. If you want to find what is the cost, simply use the iteration in the rough side, because you know as per the iteration to find the value of the cost of this t of 1, because you are going to expand it. So in place of n you put tn minus 1, like here n minus 1 in place of n I am putting here to get this one as per the iteration method. Next n minus 1 as per n we are replacing as n minus 1, that's why we are writing. The next unknown function is n minus 2 plus n minus 1 is the cost for this tn minus 1. Then we are going to expand it. When you are going to expand it, the cost will be written here. Okay, so I'm just keeping some space to write well. Now n minus 1, next cost could be like, here is the unknown term, so you can directly write this and you run for k times. Okay, now left hand side and right hand side will be written well. The left hand side is all about the number of nodes per level. Okay, here cost per level. Okay, so here number of nodes and cost per level you have to mention one by one. Level 0, level 1 and level 2, or k times, though you are running, you can say it's level k. Next, for level 0, the number of nodes per level is 1. Here is 1, here is 1, also here will be 1. How? Here it's 0, n minus 0, though is n minus 0, they have assumed that is like, we are decreasing. So we are decreasing means if something is minus with a 0, so the same value it is written. Next, minus 1, for level 1 it is minus 1, while level 2 it is minus 2. Okay, for level k it could be written as n minus k. Here the cost would be, these are the cost, n minus 1. Previously we are having in the previous videos, those who are watching this video, as my request, kindly go to the previous video, there you can get as for the constant how we are actually leveling it. Next, n minus 2, like this. Here the cost will be n minus k. Okay, here we are assuming we reach the base condition, that's why you can write t of 0 instead of this also. And t of 0, the value that we know is 0. Here is the cost we found, we think we reached it. Okay, now you have completed 50% of the problem. Okay, solutions that you have done 50%. Next, you are going for assumption. Assume you have reached the base condition. The base condition you have written is t of 0 is 0 if n equal to 0, then only it is possible. Let us think we have reached it. Okay, once you have reached it, the function, the reducing function you have written is this much, because this is the cost that you are writing. The cost is this, the function that we actually recently completed this one, how to find this function. The function will be equated, like you think your function which you got is equivalent to the base condition, then the cost will be equated then. Okay, here k equal to n. This is how you prove how many times it is running. The k you are running for indirectly n times. Okay, now you put the value of cl and ci. Okay, now cl will be number of leaf nodes or last nodes into cost per cost of each leaf or last nodes. Clear? Number of leaf nodes and cost of each leaf nodes. Done. So here what exactly we have to go for? Number of leaf nodes will be how much? Here this is our leaf node or last node. This is our cost. So leaf node will be 1 into cost of each leaf node. Cost of each leaf node is considered as 0. Okay, simple, you are writing 0. But here I told you, the bigger we are actually showing, you can show any constant because there are two different constants. So you can say one could be the answer, because I told you once a bigger is multiplying with someone, so we are just writing it instead of this. If you say, sir, can I write 0? Yes, you can, not an issue. But the constant is written now. Better we are using bigger one. Why? Because we are expressing in big O notations. That's why. Here you can write this one also. Okay. Now, our target is to find Ci. Ci is sum of all intermediate nodes. Sum of all, sum of the cost of, sum of the cost of all intermediate nodes. We are actually adding the cost. Here I think the previous sum of all the cost of all intermediate nodes we are doing. Okay, so here sum of all intermediate cost to n minus 1 n minus 2 up to n minus k, n plus n minus 1 plus n minus 2 plus n minus 3, you can take next up to n minus n minus uh, k minus 2 plus n minus k minus 1 plus n minus k, like this. Because k, why we are writing in this way, because whenever we are finding, we know the previous value will be minus. Like if you're putting, suppose you are putting the value of 3 to get the level 3 or level 2, what should be the, how many cost will be added? Suppose at level 2 you are writing, suppose k. So as per iteration which we discussed, if you do not know how iteration will work, you can check the previous videos or previous lectures. There it is clearly mentioned. The previous we can decide with the minus of this constant, because this is variable. So we are actually minus 1. So then we are getting the cost is this one. Again we are actually with that we can go for minus 1, or with this we can go for minus 2, because if you fix as k, so it is k for us, so it's k minus 1, it's k minus 2. You can check k minus 1 means if k is 2, it's minus 1 is minus 1. If k is 2 here, here is minus 1, and here if k minus 2 is there, you can write minus 0. So minus 0 have no value, so that's why we are just writing it in such way. So that is how we have completed this method. Now the kth value we decided as n. Now you substitute the value of k, n minus 1, next n minus 2 plus n minus 3, you can write, not an issue. Next n minus, in place of n k, you can write n plus n minus n minus 1 plus n minus n, you can write, because we are just substituting the value in equation 1. Okay, next, once you are substituting, I am just writing the same thing again, n minus 1, n minus 2, next n minus 3 plus dot dot. Here minus minus, then you have a plus. Okay, next n minus n plus 1, next n will be 0 here, next n plus n minus 1 plus n minus 2 plus n minus 3 up to, then you can check 2 plus 1 because your n will be discarded, 0. Okay, that you know. One formula, I'm just changing it, I'm just making it from left to right. 0 plus 1 plus 2 plus 3 up to n minus 3, n minus 2, n minus 1, n. So you know this is having a formula. The formula is 1, like the n, we are actually adding to the n, so it should be n into n plus 1 by 2. That you know. Okay, I'm just writing in the next page, that could be better to understand. Ci will be, because you are actually adding, so you can ignore 0, not an issue. 1 to n, if you're adding, that could be n into n plus 1 by 2, which is n square plus n by 2. The maximum is n square. Theoretically it is good. Okay, so then see the total time complexity is time complexity equal to CL plus CI. CL is how much? CL is 0 or 1. We are just writing 0 or 1. You can write if you are taking 1 n square, or else if you are taking the value as 0. Suppose again I'm just writing the value as 0, 0 plus n square. If you are writing, then what you are actually modifying the thing, uh, then the bigger value will be displayed. Okay, the bigger value means out of this one is constant, and this is a quadratic one that we are getting. Okay, so here quadratic is greater than the constant, that's why the time complexity, again you are writing complexity will be written as big of n square for both the cases. Okay, for both the cases n square will be the maximum for us. That's why we can write it. If in case someone is saying you, so can we write the complexity could be c plus n square? Of course yes, not an issue, because we are adding the constant here. And for this condition also, if anyone is saying, so can we write cn, like it's a bigger one, but why to go for clungy? If we know n square is bigger than everyone, but theoretically we should say it's big of n square, that's why. And I think all of you understood well. So thank you for watching this video. Have a good day. Thank you all.